Afternoon, everyone. Thank you all for coming. I'm John Dersch. I am the speaker today. It's my wife's birthday. It's my wife's birthday today. That's just why she's not here. Heaven knows she has far better things to do. Her age will not be revealed, but I will mention that her age is the answer to a multiplication table question that is frequently missed by students. We'll let it go at that. So when I was going to give a talk on E-Day, which was February 7th, 2018, 2718, and life intervened and I couldn't do it. So I thought, okay, I'll give a talk on something else. And basically, when people, occasionally people will ask me, so I want to give a talk, what should I do it on? And the answer to that is simple. What do you really like? What do you have a passion for? What do you love talking about? So I had some other ideas, and then I thought, okay, I'll do this. I don't like the title. I hate this title, but it's the best I could come up with. We're going to do two things today. We're going to talk about series. I'll show you which one in a minute. And then we're going to talk about something that seems totally unrelated, but in fact is related. Now, the series, we're going to start by adding some fractions. And basically, if you've had Calc 2, you recognize this. And if you haven't, that's okay. We're just adding up a bunch of fractions, 1 over 1 squared plus 1 over 2 squared. We're adding up reciprocals of squares. So you add up the first 3, the first 4, the first 100, the first 1,000, the first million, the first billion. It's great having Maple. You want the sum of the first billion? There it is. And what happens is you get answers that approach a uniquely defined number, which appears to be about 1.645. So the question is, well, what if you just kept going? What if you just kept adding those up forever? Or if you want to be a little more precise, you say, okay, so there appears to be a limiting value here. What is that exact limiting value? And what do you get when you add these up and you just keep going? That's what the first part of the talk is about. Now, you may already know the answer, but what I wanted to do, it occurred to me that in the many, many years that this seminar has been offered, I don't recall anyone ever going through the original derivation of this. And I thought, okay, this would be an interesting thing to do. So we are going to do that. Now, this problem, what is the exact value of that? First studied by Pietro Mengoli. Dom is here. Fantastic. Am I pronouncing that correctly? Mengoli? Does that mean yes? And then he was around 1650. He considered the series, was not able to solve it. He was at the University of Bologna. Is that correct? I wasn't going to say Bologna. Okay. He was, as near as I can tell, he was the first person to actually look at this might be an interesting problem to study. Some very prominent names, mathematicians, looked at this series. Leibniz, one of the co-founders of calculus, a couple of the Bernoulli brothers, Dumois, and others attempted to find the sum and were unable to do so. Bernoulli's, both of them were at the University of Basel. It's in Switzerland. And so finding the exact sum became known as the Basel Problem. And it just so happened that Johann Bernoulli had, as you could kind of say, a student, this guy named Leonhard Euler. Some of you may know Radu Teodorescu, a longtime faculty member here, adjunct here. And Radu, whenever he heard Euler's name, he would say, that guy is amazing. And Euler was amazing. He solved the Basel problem when he was at the University of St. Petersburg in Russia, published his solution in 1735, and one of the things I read said that he came across the solution quite unexpectedly. So in other words, it sounds like he didn't sit down and say, I'm going to solve this. He was in the midst of doing something else, and this just sort of happened. Exactly when it happened, not sure. Published in 1735. There is evidence to suggest he discovered it in 1732 and maybe even earlier than that. What we're going to do is look at what he did. Now, that has to be taken with a grain of salt because I have half a dozen books that purport to show what he did, and they're all a little bit different. I'm going with this one because I liked it. Okay. Euler's derivation. Now, he starts right away with this, and you're thinking, well, yeah, that's where I'd start. This seems to have nothing whatsoever to do with that because that's the sum of the reciprocals of squares, and this involves higher powers and factorials, and I'm going to put a couple things up here because, you know, I'm not familiar with everyone in the audience. I don't know what your math background is, so just a reminder of a couple of things. That notation, if you have 3 factorial, that does mean 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1, and so on. Why he started here? He was Euler. He had incredible insight. He either just knew in his gut that it was going to work or came across it unexpectedly. He's working with something else, realized that this is going to be helpful, and ran with it. Now, did a little algebra here. If you take p of x, multiply top and bottom by x, assuming, of course, that x isn't 0, when you multiply the top by x, you, of course, get x, and then x squared times x is x cubed, x to the 4th times x is x to the 5th, and so on. You get this on top, and since you've divided by x, you get x on the bottom. And you may recognize, again, depends on what math you've had, but this might look familiar. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. That is the series for sine x. And so p of x can be written as sine x over x. Now, that means that if you want to find the zeros of p of x, they're the same as the zeros of sine x. Now, when we talk about the zeros of a function, we're talking about the values of x that make the function 0. And for the sine function, you recall that for the sine function, you just draw your basic sine wave. Never looks quite as good going in the other direction. And we're not counting 0 because remember x isn't 0. Zeros of the sine function occur at pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi. Zeros of the sine function occur at multiples of pi. Okay? Well, since this fraction is 0 only when the numerator is 0, the zeros of sine will be the same as the 0 of this p of x. Now, p of x, you remember, it's this. It's just a, and this is Euler, this is how we think of it, just an infinitely long polynomial. It's just a really long polynomial, okay? So if you talk about zeros of a polynomial, that automatically leads to factors. Now, factor theorem, if you recall, if z is a 0 of some polynomial in x of p of x, then Euler wanted to write it like this. 1 minus x over z is a factor of p of x. You may not be used to seeing it like this. You might be used to seeing it like this. Essentially, as I tell my calc students, you can factor anything if you want to badly enough, and you can factor and you make this look like that. But we're not going to do that. We're just going to leave it the way it is. Okay? So Euler knew because these are zeros that these would be factors. So p of x has those as factors, and because p of x is just an infinitely long polynomial, you can factor it. Okay? One of the zeros is pi, another one is negative pi, another zero is 2 pi and negative 2 pi, 3 pi, negative 3 pi, so you can write it. You can write p of x as an infinite product of factors. Now, you and I might be concerned about what is this infinite product thing and does it even make any sense? Euler just went, oh yeah, it's fine, and kept going. Well, his intuition was astonishing. Everything that you're seeing here is supposedly exactly what he did. And everything that you're seeing here does have modern theoretical justification. It's not like he got away with something. His intuition was superb. Everything he did was correct. He just didn't bother to prove it. Okay, so then what do? You double negative is positive, double negative is positive. And then, so binomial times its conjugate, no middle term, you get the difference of two squares. Binomial times its conjugate, difference of two squares, so you get this, and this, and this, and that. Forever, all multiplied together. So that's p of x. Well, now that means we have two different representations of p of x. We have this representation of p of x, which Euler came using the zeros of the sine function. Euler got using the zeros of the sine function. And we have this representation of p of x, because that's how Euler defined it originally. Well, if those are both representations of p of x, then they have to be equal. This has to match up with this. Remember now, he's thinking of these as infinitely long polynomials. So corresponding terms have to agree. In particular, the x squared terms up here have to agree with the x squared term down here. The x to the fourth terms up there have to agree, and so on. So what Euler did is he removed parentheses on top and grouped terms by powers of x. So now we have to pause for a moment and ask ourselves, especially for those of you who teach, imagine going into an algebra class and saying, we have this product of infinitely many factors for class. For homework tonight, I'd like you to multiply that out. It could take some time. All right, so Euler being Euler, maybe to him it was just obvious. I'm not in the realm of thinking stuff like this is obvious. So when I do this, I have to multiply like mortals do. I have to multiply things two at a time. So if you actually take a couple of minutes to look at what happens if you multiply, just the first two. Let's see. You get 1 times 1. You get 1 times this with a negative in front of it, so that's negative x squared over 4 pi squared. You get 1 times this one, so that's a negative x squared over just pi squared. And then, of course, those two together, you get plus x to the fourth over 4 pi squared times pi squared to be pi to the fourth. Okay. Actually, I don't want to write equals there, because I'm to conserve a little bit of space here, I'm going to take these two. I got an answer to that. I'm not going to combine those because I don't understand how to subtract fractions anyway. I knew you'd like that, Dana. So now I'm going to take the product of those two and multiply by the next one. And okay, so 1 times 1. And then you get this one and this one times 1, and you also get 1 times this. So basically you're going to get 3x squared terms. Let me do this one first. 1 times this, you get the negative of x squared over 9 pi squared. And then you get 1 times this, so you get the negative of x squared over 4 pi squared. And then you get the negative of x squared over just pi squared. Okay, so those are x squared terms. Those are all the x squared terms you're going to get here. Now you get other stuff. This x squared term times this x squared terms times this. That'll give you x to the fourth. You have x to the fourth times that. You're going to get some x to the fourth terms, which I am not going to write down, because Euler didn't need those. So plus x to the fourth terms. Plus, and then you'd also get an x to the sixth term. Okay? And one more. If you multiply that by the next one, which is 1 minus x squared over 16 pi squared, then you get 1. And then you get the negative of x squared over 16 pi squared times 1. You get minus x squared over 9 pi squared times 1 minus x squared over 4 pi squared times 1 minus x squared over pi squared. Those are all the x squared terms. And then you get a bunch of x to the fourth terms, you get a bunch of x to the sixth terms, and you're going to get an x to the eighth term. So we just say, okay, we do this. Well, you get the idea. You're going to keep getting x squared terms that all look the same, except the denominators are pi squared, 4 pi squared, 9 pi squared, 16 pi squared. The next one's going to be 25 pi squared, and 36 pi squared. So that just keeps going. So, is that all right? So, you get p of x is this, plus the other stuff. But remember, p of x is actually this. So, equate x squared terms. This right here has to equate to this. If these two polynomials are really the same, and Euler knew they were, these two have to match up. So, match them up. This is just so cool, okay? Because look, you match these up, pull out the x squared, right? You got a common factor of x squared here. Pull it out. You can divide by x squared because x isn't 0, right? So now you have this. So 1 over 3 factorial is equal to this. I think I'd like to factor pi squared out of each of those. What do you think? It's in the denominator, so I got to factor out 1 over pi squared. So now I have that. Oh, look. Look. Well, now, 1 over 3 factorial, 3 factorial 6. So I got 1/6. I pulled out the 1 over pi squared. I have that remaining. So that remaining is just pi squared over 6. And well, wait, that's it. This sum is pi squared over 6. Yes, and we are all applauding Euler because to me, it is phenomenal that he could take all these ideas and put them together, and it's like, wow. That's it. Now, that's not the entire talk because we've only been here 20 minutes, and I know you'd hate to leave early. Just like students in my classes, when I let them out early, which happens a lot, they get really disappointed. Okay, so we have that. Is there any part of this that you'd like to look at again or you have a question on? I mean, this may be the first time in my life I've given a seminar where I'm going to get done early, okay? Because there is a part 2, but that's not going to take very long either. You have any questions right now? Or anything we just did?
So what happened to
Yeah, so Euler being Euler, you know, it's like, yeah, that's pretty cool, but, you know, I kind of found that unexpectedly anyway. So what happens if you do something with those x to the fourth terms that I was too afraid to write out? Well, you have x to the fourth terms on this side, you have x to the fourth terms on the p of x side, you equate the coefficients of the x to the fourth terms, and you are able to show that the sum of the reciprocals of the fourth powers is pi to the fourth over 90. I can tell you, just from me messing around with it a little bit, that the algebra involved there is really bad. And it only gets worse. I mean, this is not bad. You can see the pattern right away. And that's what you're looking for. You're looking for a pattern. You start multiplying out and collecting the x to the fourth terms, it's not real obvious. And I'm not real clear. Well, okay, I think I know a better way to handle that. Let me say more about that in a minute. So you have this, etc. Because Euler found a formula that gives exact values for all even powers. In other words, not just 1 over 1, not just 1 over squares or 1 over fourth powers or 1 over sixth powers, but 1 over any even power. Now, I didn't put that formula here because it involves Bernoulli numbers, and Bernoulli numbers are interesting but not very transparent. That would almost be its own talk. So if you really want to know what that formula is, I can provide you with references, or you could probably just, you could Google it. But he did give a formula for all exact power values of even powers. There is a reference that I ran across which actually had him writing down what the sum is of 1 over, not sixth power, but 26th power. And exactly, and it's a fraction like this long, which of course it's 1730 something. He did this all by hand. It's phenomenal. But what I find particularly interesting is, okay, these are all even powers, right? And of course, when you look at this, it's all even powers. What about odd powers? What about this? The exact value, now the approximate value of this, that's Calc 2 problem. My Calc 2 students get problems like this all the time. Approximate this, but the exact value, no one knows. Exact value is unknown. In fact, the exact value for any of the odd powers to this day is unknown. In fact, it's not even known if you add up the reciprocals of odd powers, fifth power, seventh power, ninth power, and so on. It's not even known if those are rational or irrational. It is known that this one is irrational, but no one knows the exact value yet. If you're looking for something to do in your spare time. All right, this is the end of part 1. Part 2. So I didn't give the talk in February. What I want to give another talk on. I had some other ideas that were kind of interesting, but for one reason or another, I just didn't think they'd be very good. And then I thought this would be great, but it's like, well, yeah, but this is not going to take an hour, and it took 25 minutes. So, well, what could I do? And then I remembered something from a long time ago, and that's what gives rise to this. This is part 2. And this is completely different. There is zero calculus here. Okay. Suppose A and B are natural numbers, counting numbers, 1, 2, 3, 4, so on. We don't include 0 here. We let GCD of AB denote the greatest common divisor of A and B. That's defined to be the largest natural number that divides both A and B. And of course, what we're talking about here is divides A and B means that it goes in evenly. There's no remainder. So, for example, you let A equal 18 and B equal 24. Greatest common divisor of A and B. Greatest common divisor of 18 and 24. It's the biggest number that goes into both evenly, and that would be 6, I hope. Yeah, that's right. Now, if you change it just a tiny bit, 18 and 25, completely different answer, because the only natural number that goes into both of 18 and 25 evenly is 1. Well, it turns out that if you have two natural numbers, and if their only common divisor is the number 1, then we have what are called relatively prime numbers. So A and B be natural numbers. If the greatest common divisor of A and B is 1, we say that A and B are relatively prime. Relatively prime doesn't mean prime. 18 and 25 are relatively prime. Sometimes they're called co-prime. They're certainly not prime numbers. I mean, 18 isn't prime, neither is 25. But the greatest common divisor of 18 and 25 is 1. So 18 and 25 are said to be relatively prime. 18 and 24 are not, because you can divide them by 1 or 2 or 3 or 4 or 6, I guess. Okay, so relatively prime means the only natural number that divides both of them is the number 1. So suppose you choose A and B randomly. You just pick two natural numbers at random, and they could be the same number. I mean, if they're chosen at random, it's possible it could be the same number. What's the probability that those two numbers are relatively prime? So pick two of them. What's the probability they're relatively prime? Now, I've written this in different ways. This is just an abbreviation. This is another way of writing it. A and B are relatively prime means the greatest common divisor is 1. And this is something that's going to come in handy in a few minutes. I'm going to let P equal the probability that the greatest common divisor of A and B is 1. What's that probability? What's P? Our goal is to find P. And it'll be useful maybe later for me to write down that definition of P here just so we have it as a reference. So let's see. P is the probability that the greatest common divisor of A and B is 1. Our goal is to find P. I can't remember the details, but I first heard of this problem a long time ago. I was a student, so yeah, a long time ago. And it seems like I saw a proof of this, and I didn't understand most of it, which is, probably just because it's me. But I remember it being lengthy and intricate, and I thought, I wonder if I could come across a proof that wasn't so lengthy and intricate. And I'm going to be really very clear about this. What you're about to see is not my original proof. It's not. I think I've made it a little more understandable, but I do not want to claim, yep, I did this, because I didn't. I'll show you where I got it from. Here's how we can find P. We need a lemma. A lemma is a theorem that basically proves something useful. Maybe it's kind of technical, and you want to use it later to prove the main result. So we need this result so that we can figure out what P is. Now the lemma, A and B are randomly chosen natural numbers. P is, as stated, let n be any natural number. Then the probability that the greatest common divisor of A and B is n is P over n squared. Now let's stop for a minute here. P, which is what we want to find, is the probability that 1 is the largest number that goes into both A and B. The lemma is going to show that the probability that n, where n could be 1, I mean, n is a natural number, it could be 1, it could be 2, it could be a billion. The probability that n goes into both A and B can be written in terms of P. It's P over n squared. Now, if n happens to be 1, n is any natural number, it could be 1. If n is 1, this becomes p over 1 squared, which is p, which agrees with this. So in a sense, we're proving a more general statement here, in a sense. Okay. Now, it took me a little while to unpack this in a sense that made sense to me. But then I realized that when you say the greatest common divisor of A and B is n, what you're really saying is that there are 3 things that must be true. If the greatest common divisor of A and B is n, then 3 things have to happen. N has to go into A, and n has to go into B, and nothing bigger than n goes into both A and B. All 3 of those have to be true. So the probability that the greatest common divisor of A and B is n is basically a compound statement. It's an and statement. Well, 2 ands, 3 statements. It's the probability that n divides A and n divides B and no number greater than n divides both. Those are independent events. The occurrence of one has no influence on the occurrence of the other, and so those probabilities multiply. Probability n divides A times probability n divides B times probability that no number greater than n divides both. So what we need to do is determine this probability and this probability and then that one. Now, the first 2 are pretty straightforward because, I mean, if you think, okay, what's the, so let's get context here, okay? Originally, you choose 2 natural numbers, A and B. So you've chosen a natural number A. Okay, what's the probability that some number n divides it? Well, it depends on n. Here, this probably isn't necessary, but just so I have something to look at here. So you list a few of the natural numbers and you start thinking about what it means to have something which divides those, and you start talking about probabilities. Suppose n is 1. What's the probability that 1 goes into A? 100%. All numbers can be are divisible by 1. Okay? So that would be 1. What's the probability that 2 divides A? Now remember, A is completely randomly chosen. What's the probability that a completely randomly chosen counting number is divisible by 2? 50%, because half of all of these numbers are even. You know, 2, 4, 6, half of them are even, so yeah, it's a half. What's the probability that 3 divides A? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every third number is divisible by 3, right? So it's 1/3. Probability that 4 divides A, every fourth number, 1/4. Probability that 5 divides A is 1/5. Probability n divides A is just 1 over n. So this is 1 over n. This, B is just as random as A, so this is 1 over n. That's also 1 over n. That last one's kind of interesting. So we have this. Probability n divides A is 1 over n. Probability n divides B is 1 over B. Probability that no number greater than n divides both A and B, well, drop that down by a factor of n. The probability that no number greater than n divides both A and B is the same as the probability that no number greater than 1 divides A over n and B over n. N times smaller, n times smaller, n times smaller. But if A can be divided by n, then this is a natural number itself, and this is a natural number itself. The probability that no number greater than 1 divides a couple of natural numbers is the probability that their greatest common divisor is 1, and that's P. probability that no number greater than n divides both a and b is equivalent to this. This, by our definition, is exactly p. And so I have 1 over n times 1 over n, which 1 over n squared times p is this. And that's the proof of the lemma. Doing okay with that? Questions? Starting to look tired. You look like my normal classes. It's like, oh, geez, is he ever going to shut up? Don't have too much more time here. Man, this is going to be wonderful. I'm actually going to get done early. This is all right? Because now here's what we have. Because we have the probability that the greatest common divisor of AB is n, that probability is p over n squared. I actually want to write that down here, just because I know how close we are to being done. And we, of course, are going to need to use this. And the way we're going to use it, this is the sort of stuff I live for professionally. Okay. Back to our goal. A and B are randomly chosen natural numbers. Find P. We state the obvious. What's the obvious? Pick two natural numbers. The greatest common divisor exists. Now, mathematicians are sometimes really big on proving existence theorems. I think we'll just accept this one. You have a couple of natural numbers. Is there going to be a largest number that goes into both? Yeah. Yeah, I think we can expect that to be true. So what that means is the probability that the greatest common divisor of AB exists, that probability is 100%. We know there's going to be a greatest common divisor for two natural numbers A and B. There's 100% certainty that that's going to happen. So I want you to look right here. This is 1. Okay? You ready? So that's 1. Here it is. Well, let's see. What could the greatest common divisor of A be? What could that be? Well, it could be 1. It could be 2. It could be 3. It could be 4. It could be 5. I won't keep going. So it's the probability the greatest common divisor is 1, or it's 2, or it's 3, or it's 4, and those are OR statements. Those are OR statements. They are also disjoint OR statements because it is impossible for the greatest common divisor to be both 1 and 2 at the same time. That falls under the heading of a uniqueness theorem. We're also not going to prove that the greatest common divisor is unique. It is. Okay. So let's see. When you have probabilities, and Jen is here, so I got to be really careful I don't screw up. I already didn't do any good jokes for you. I'm sorry.
I like the white one. That was pretty good.
Really?
Yeah.
Which one?
No, about how she's not here. That's her birthday present.
That wasn't a joke. I was kind of sad that she wasn't here. I mean, you know, she did attend a math talk of mine once. I am not going to talk to YouTube about this, but I can tell you more about that later. So these are OR statements. On Harris is here too. We got statisticians in here. I got to be careful I do this right. When you have disjoint statements, their probabilities add. So this probability plus that probability plus that probability plus that. And you notice this goes on forever because, I mean, you know, greatest common divisor could be 1 or 2 or 3 or 4 or 5 or 100 or a billion or a Google. I mean, it never ends, okay? Well, now, remember our lemma? The probability that the greatest common divisor is n is p over n squared. So 1 equals the sum of those infinitely many probabilities. This one is exactly p over 1 squared. This one is p over 2 squared, p over 3 squared, p over 4 squared, and so. One is equal to p times that sum, and that sum is pi squared over 6. when I was trying to I told you I didn't like the title for this talk. When I was trying to come up with a title, one of the titles I had in mind was "That Can't Be True," because when a student from about 6 months ago, when I first thought I might do this, heard about this, she said, "That can't be true." Now that'd be a good title, and I didn't do it. I don't know why. Now we're not quite done, of course, because we haven't found p. But I think we can do the algebra on that, and p is 1 over pi squared over 6. It's 6 over pi squared. The probability that a and b are relatively prime is exactly 6 over pi squared, which turns out to be a little less than 61%. Now, it constantly amazes me how much of mathematics is related when you don't think it would be. That was going to be another title for the talk, which was "It's all related." I didn't like that one either. Now, just to close things up here, there's been some talk on the internet about the Riemann hypothesis and how perhaps it's been proven and perhaps not, and I'm just going to sit back and wait. But, okay, Riemann hypothesis has to do with the Riemann zeta function. Now, the Riemann zeta function for us here, we are assuming that the input variable is just a positive whole number. In fact, it's actually 2 or larger. The Riemann zeta function is defined to be this. So zeta of 2 is the sum of the reciprocals of squares. That's pi squared over 6. Zeta of 4 is pi to the 4th over 90. Zeta of 3 and zeta of 5, we don't know the exact values for those, but we can approximate them, and they are roughly these. Okay, so why bring this up? Because what if you randomly choose more than 2 natural numbers? What if you choose 3 or 4 or n? The probability that all n of those are relatively prime is 1 over zeta of n, which means that what we just did here, this, generalizes to, Okay, so this, remember, this is the sum of the reciprocals of the squares. This is the sum of the reciprocals of the cubes, 4th powers, 5th powers, and generally nth powers. It's true. Now, from what I understand, the proof that this is true for n numbers is quite challenging, partly because it involves a lot of ideas that we generally don't cover in the first 2 years of college mathematics. And so if you're going to ask me, do you know how to prove that? My answer is no. I've seen some proofs of it, and I don't understand quite a bit of it. Maybe, so if one of you knows how to do that, that would be an excellent follow-up talk sometime. So yeah, it is incredible. That's the end of part 2. Do you have any questions here? I have a couple references I want to share with you. Any questions at all on what we did here? It was hard to choose a reference because, like I say, there's probably half a dozen different ways of finding out how Euler proved it, but I decided to go with one of the best books ever written on mathematics. I know it's one of Mr. Lee's favorite books, Euler, the Master of Us All. That book has been out almost 20 years now, which is hard to believe. And pages 47, 48, basically the proof that I showed you was pretty much what Dunham has. Okay, remember I told you that when I saw a proof of the probability of greatest common divisor is 1, when I saw that proof, I was baffled because it was very lengthy and very technical. In 1992, there appeared a very short article in the College Mathematics Journal. That's part of the Mathematical Association of America. It's one of their publications. I mean, the article is, I'm not making this up, it's this long. That's it. Okay? And so I took that and tried to make it a little more understandable, because when you read a proof that's that long, you know you're in for something because they're condensing a lot of stuff, okay? If you've taken upper level math, short proofs are not your friends, because usually it's like, wait, what? Okay, but look at this. Original proof by Aaron D. Abrams and Matteo, J. Paris. He was 16 and he was 17. They were students at University of California, Davis. A 16 and a 17-year-old came up with that brilliant idea. It all hinges on this. The lemma, it's incredible. That's incredible. So, that's all I got. Look at that, 15 minutes early. Thanks for coming. Now, I've already asked if you have questions, so I suppose I should ask again. You probably don't, but if there is anything you want to know about, or you want to find out if I know about it, or if you think maybe I know where you could find it, then you can ask.
What is Euler Master of Basel? Is it like a biography, or is it a kind of culmination of?
Well, Mr. Lee, how would you characterize that? What kind of book is this? Is this biographical, or is it more the math that he did? Combination? Okay. Yeah, I have copies in my office if you'd like one. Yeah. Yes?
So Abrams and Paris, 17 and 16 when they did this in 1989, they got to be still alive. Are they doing anything?
I tried to look, and and I'll be honest, I tried to look, but I didn't have a lot of time to do it. I believe I found Abrams, and I believe, and I should have written it down, it escapes me. He's a math professor somewhere. But I got to be careful because that's not that uncommon of a name. I don't know if it's this Aaron Abrams. Pretty good chance. He's a math professor at some university, I forget which one. I couldn't find him, but that's largely because I probably didn't look hard enough. So, oh yeah, they're still around, I would imagine. I mean, that's only 29 years ago. They actually wrote it up in '89. And publication delays being what they are, it was about 2 years later, January of '92, when it was finally published. Yeah, I wondered about that too, and in my spare time, I'll see if I can find out more. Anything else? Dana, you looking right now? Yeah, see, it's the problem with cell phones is like they're distracting, because when he ought to be hanging on my every word, he's just on his phone. Are you getting all this? Are you recording all this? Good. That's good. Yeah. Anything else?
He's running your talk through Turnitin, or what is it, Turnitin?
Well, you're going to find references, because like I say, I do not claim, there is no way that I have the creative powers to come up with the kind of proof that Abrams and Paris came up with. It's just wow. Because the proof I saw took 45 minutes. The proof you folks just saw with me, talking about it was what, 15 or 20? And it could have been made shorter than that. So, yeah, it's amazing. Okay, you got other questions hanging around. Now we have another speaker coming in October. October 30th, we're going to have, and I have to make sure I get the right name here, Riemann Muhammad from Ohio University. Actually, someone Ms. Vandermeer knows is going to be coming into town, and he's going to give a talk on Islamic art and patterns in geometry. I think it's going to be very cool. That will be October the 30th, which I believe is a Tuesday, and more information will come about that probably in a couple of weeks. Oh, and I should mention that we have in our audience someone who's trying to hide right now, who will be giving a talk in November. I won't, if you want to say something about that now, that's fine, otherwise you can wait. You want to wait? She's going to wait. Okay. What's that? Yes, well, got to give people a reason to come back, right? All right. And if you're ever interested in giving a talk, or you know someone who wants to give a talk, it's really, I'm serious. If you find something you think is cool, that's what you do. So, okay. Thanks a lot, everyone.